In this video segment, we'll talk about applications of haptic technology. There are a lot of existing applications of haptics. It's not a brand new field as a term that people are familiar with. It's been around for at least 20 to 30 years. One of the most obvious application areas is entertainment, and a form of haptic feedback that people are very familiar with is vibration feedback. Some people call this the poor man's haptic feedback because it's not as sophisticated as the kinesthetic haptic feedback that you'll be using with your HapKit in this class, but nonetheless, it's a very useful, cheap form of haptic feedback that can really enhance your engagement with a virtual environment. So this is a picture of a Nintendo Wiimote, and when you play, say, virtual tennis with the Wii and you swing the Wiimote back and forth, and you hit the tennis ball, the Wiimote will vibrate. There's simply a small vibrating motor inside the Wiimote that will shake upon the virtual impact with the virtual ball. That vibration really enhances the feeling of having made a contact. It tells you that an event occurred, and it can actually mimic the kinds of vibrations that you get when these events occur in the real world. So this sort of use of haptics in entertainment right now is mostly restricted to vibration feedback, but there are definitely video games that you can play which provide force feedback on a joystick or even force feedback on, say, a fake motorcycle that you could sit on. Another application of haptics is education. So this class is just an example of educational haptics. And this picture here is from Johns Hopkins University, where some haptic paddles, a predecessor to the current HapKit, were used to teach students about dynamic systems and controls. Another form of education, which is more in the professional realm, is medical simulation. This is an image from the University ETH Zurich, where they created a simulator for a medical procedure. And what the surgeon is doing here to practice doing the medical procedure is holding onto some manipulators which are attached under this sheet, which represents the covering of a patient. It's attached to a real kinesthetic or force feedback haptic device, which is providing this surgeon with forces so it feels like he's doing real surgery. In addition, there's a graphical display which shows what he would normally see through the endoscopic camera that would be going into the patient. The idea behind haptics in this sort of professional training is that you would like people to train in environments that are as realistic as possible, and a purely visual or graphical environment isn't going to provide the same sort of training as a hands-on haptic device will. And of course, you would like your surgeon to be as well trained as possible before you go in to have surgery, right? Just like airline pilots train on flight simulators, there's becoming more and more of a push for surgeons to train on immersive haptic simulations. Another wide array of applications of haptics occurs in all sorts of human-computer interfaces. One example is on BMW 700 series, as well as some other cars. There are haptic devices that the human driver can interact with to control a number of features on the car. So this iDrive right here is a knob, which is essentially just stuck onto the top of a motor. And when you turn the knob, you can get a variety of haptic sensations like clicks or vibrations or smoothly changing forces or a damping viscous field. And each of these forms of haptic feedback can represent controlling different features of the car. For example, the temperature, changing the radio station, or the amount of air that's coming out of the air conditioning. So the idea is that if you could give the driver haptic feedback, then maybe they can spend more time with their eyes on the road and less time trying to look at a variety of buttons and dials. Of course, you're probably familiar with haptic feedback on your cell phone. One of the most obvious forms is that when someone calls and you have your cell phone set to vibrate, you can feel a vibration. But there are many companies, Immersion is one example that works with a lot of cell phone companies, which are developing haptic feedback for phones that are a little bit more sophisticated. For example, it could vibrate differently depending on what ringtone you selected. There are companies which are making bumps appear on the surface of phones that can allow you to get a tactile display over the screen. And in the long run, people are going to want phones and iPads which really provide force feedback over the screen rather than just vibration or tactile feedback. Another interesting example of a human-computer interface that is really used to increase productivity is an example that has been used at Boeing. What they've done is created virtual environments where you can essentially design a plane without building it. Of course, they do build and test, but in the initial design stage, it's very cost-effective to be able to design the airplane in a virtual environment. One of the problems with designing in a virtual environment, though, is that it can be difficult to get an intuition for whether certain tools or parts will fit into the configuration that they need to be in the final plane. So one example is if you want to be able to reach a tool in to repair a part, it might have to go through a very circuitous path in order to get there. You can use a very strong computer to take lots of time to try to figure out if such a path is available, but this does take a lot of time, and it turns out people are really good at finding such paths. So they've had engineers bump around in a haptic virtual environment to try to find these paths in order to expedite the process of figuring out if a certain tool will fit in a location. So that's a very practical form of human-computer interface, which is helping us solve computational problems in a faster, more straightforward way. Of course, the long-term goal is that we would like to have haptic virtual environments that can create any sensation that we want at any amount of magnitude. And so just to let you dream a little bit about what we could do with the perfect haptic interface, you should think about what if you could make any surface around you change its haptic properties. So instead of hard, it could become fuzzy. It could become sticky or soft. What would that mean in terms of entertainment or utility or productivity? What if you could touch priceless works of art? Right now you go to a museum, you can look, but you definitely can't touch. And sculpture in particular is an interesting example where interesting textures and surfaces and shapes sort of beg to be touched. There have been researchers who have developed virtual museum experiences that let you sort of poke through a virtual stick, through a kinesthetic haptic device at a sculpture in order to experience it. But would it be ever possible to make this a more immersive experience that could really truly allow you to appreciate art in a new way? Finally, for the Star Trek fans out there, I'm sure you're familiar with the holodeck, the idea that you could go into this virtual world and simulate experiences that might teach you something. Well, the holodeck really isn't going to work properly unless you have haptic feedback. Imagine going into that holodeck without any cutaneous or kinesthetic feedback. You would be truly impoverished and impaired and not be able to do all the kinds of things that they simulate doing on Star Trek. And so if you want to create truly immersive and interesting virtual worlds, you need haptic feedback. Would you need full body suits? Would you have objects that magically, physically generate forces in the world? We don't know what a truly haptic holodeck would look like yet, but you can think about what sort of haptic devices would be needed to create one. Finally, we're interested, in my research group in particular, about what haptics can teach you. This is part of the reason that I'm teaching this class, is that a lot of online learning is purely about clicking through things on the computer. But for me, hands-on learning is really important. We've seen this a lot through our experiences in doing outreach programs. So here's a video of a bunch of kids at Warm Springs Elementary School in Fremont, California, interacting with haptic devices at one of our demonstrations. These are haptic paddles, which are similar to the HapKit, but a little bit different. And these kids can't wait to get their hands on these haptic devices. They're teaching them not only about haptic technology, but also about the underlying physics of springs and dampers and mass in a way that they can actually change some of the mechanical properties of those virtual environments and then feel directly how they change. So haptics, I think, has a great potential to teach people not just about technology, but about underlying physics or even other topics. So here's some examples from engineering education which underscore my point. James Stice wrote an article that's very well known in the engineering education literature that you remember more and more about what you learned if more and more senses are engaged. So we'd like to ask the question about how much will you retain when you interact with something and you feel it. Now I'll talk about the basics of how haptic virtual environments as well as how haptic teleoperators work, because this is going to be essential for you to understand why we design haptic devices the way they do and what they're capable of. In this picture, we have a user, one of my graduate students, Ann Majewicz. She's interacting with a commercial haptic device. In this case, it's the Phantom Omni, now also called the Magic Touch. And she manipulates this end effector in order to move this haptic interaction a point around in the physical world. However, she's not just feeling the mechanism itself, she's feeling a virtual world which is being represented in the computer that's controlling the motors on this haptic device. So her movements are being translated over here to a virtual environment where her haptic interaction point is being represented by this little red cursor. And she can touch this virtual teapot and it will generate forces that push on her so it feels as if she's really touching something. Now this is the virtual environment which is housed in the computer, and so there's simply a computer program which is saying, based on how Ann moved, how much force should I apply? Once those forces are calculated, then they're sent back to the haptic device in order to actually push on Ann's hand. And that's the rendering of haptic virtual environments. Although we'll only be doing virtual environments in this class, haptic teleoperation is also really exciting. First, I'll mention one other type of haptic device, which is a form of virtual or augmented reality, because this is another type of haptic device which is quite different from the kinesthetic display shown in the last slide. This is my student Michelle, who was wearing a device that we call Happy Bands, or Haptic Augmented Posture Interface. And each one of these bands includes an accelerometer, which helps measure her orientation of that limb segment, as well as little vibrating motors, similar to the kind that you find in your cell phone, that give her haptic feedback in different locations on the arm and tell her to move in one way or another. A Microsoft Kinect is tracking the motions of her overall body and translating that to this image that you see on the screen. And based on how she moves versus where the system wants her to move, for example, to achieve a certain yoga pose, she's getting vibration feedback that will push her in one direction or another, or not actually push her, but indicate that she should move. So this is just a very different type of haptic device, which is more cutaneous or tactile in nature, and it's wearable rather than a manipulandum like the one that Ann was using in the previous slide. Now we get on to haptic teleoperation, and we get back to Ann interacting with her Phantom Omni haptic device. What she's doing is still holding onto the haptic device whose motion is being recorded, and now that motion is being sent not to a virtual environment, but to a robot that's being controlled in the real world. And this robot is trying to follow her movements of the master. Her haptic interaction point now, it could be anywhere on this robot, but we've put it here in the middle of the hand, is going to be her location in the physical world in this remote environment. And if this robot were to say to contact a virtual environment, like a wall here, then it would generate a force on the haptic interaction point, which she would then feel on the master side. So in haptic teleoperation, you're replacing the virtual environment with a real robot. There are a lot of interesting teleoperation scenarios. For example, the Canadarm, which has been mounted on the space shuttle, as well as on the International Space Station, can be teleoperated by a human operator who's sitting locally near the arm. And this allows astronauts to be able to accomplish things in space without doing a spacewalk. Spacewalks are extremely dangerous, and so if it's possible to stay inside the vessel and control the arm remotely, then that really increases the safety for the astronaut. Another example, which has a lot to do with safety, is explosive ordnance disposal, or bomb robots. In this case, soldiers use teleoperated bomb robots in order to explore environments that they think look suspicious, and they could even decommission a bomb. And this ideally would be much safer than a person going to do this by hand. One of my favorite applications of teleoperation is teleoperated robot-assisted surgery. This is an image of the Da Vinci surgical system, which is a teleoperated surgical robot where a human operator manipulates a master joystick, essentially, and controls the remote robot. And if you were able to sense forces on the patient's side and feed them back to the master, we hypothesized that would improve performance. Now, all of these teleoperation scenarios shown here don't necessarily have haptic feedback in daily practice, but this is one of the great potential areas of haptics, is to improve teleoperation procedures in all of these mission critical and dangerous and important for health type of environments. I'll talk a little bit more about teleoperated surgical robots because this is my area of expertise. This video here is a close-up of what a surgeon would see when they use the teleoperated Da Vinci surgical system. And I should note these videos are provided by Intuitive Surgical, who also supports some of the research in my laboratory. In this system, the surgeon manipulates these master manipulators, and the remote robot tries to follow those movements in order to interact with the tissue. This is fake tissue, by the way, lest anyone get queasy. It's just plastic and foam. And what happens when you see the split screen that will come up in a minute is that you see how the motion of the remote robot over here is imitating the motion of the master robot. But the important thing to note is that these two images, they're not at the same scale. So in this bottom image, this distance is probably on the order of 10 centimeters. But in the top image, that same distance was on the order of 1 centimeter. So you can imagine that by scaling the operator motions down, you make the user more accurate. I'm not going to talk about how we do haptic feedback in a scenario like this because it's not yet clinically implemented, at least not in a way that you could feel the minute forces of interacting with these sutures. But that's an interesting and open area of research that, as I mentioned, has a lot of potential.